You know, sometimes a huge scientific revolution doesn't come from some massive, dense textbook. Nope. Sometimes it's just a few pages. And today, we're going to look at one of those moments. A single paper from 1929 that just completely redrew our map of the entire cosmos. So, let's get into it.
So, this is it. A relation between distance and radial velocity among extra-galactic nebulae. Pretty dry title, right? It was written by the astronomer Edwin Hubble, working out of the Mount Wilson Observatory. And yeah, I know, it doesn't look like much, but trust me, buried deep inside this data is a discovery that would reshape literally everything we thought we knew about the universe.
And Hubble, he gets right to the point. He says the results establish a roughly linear relation between how fast something is moving and how far away it is. So what does that actually mean? Well, put simply, the farther away an object is, the faster it seems to be flying away from us. That's it. A simple observation, right? But with truly cosmic consequences.
But why? Why was that so important? I mean, what did that simple pattern actually reveal about the cosmos? Well, to really get it, we need to rewind a bit. We've got to look at the puzzle that had astronomers totally stumped back in the 1920s.
All right, so let's set the stage. The main characters in this whole story, they're these things called nebulae.
See, back when Hubble wrote this paper, the term extra-galactic nebula was still pretty new. For centuries, astronomers just saw these faint, fuzzy smudges in their telescopes. They had no idea what they were. But right around this time, they were just starting to realize these weren't clouds of gas in our own galaxy. No, they were immense, distant island universes, entire galaxies, just like our own Milky Way. And here's the thing. These galaxies were moving. Some seemed to be coming towards us, others were flying away. But their movements just seemed chaotic, a total mess. As Hubble himself puts it right in the paper, all the previous attempts to find some kind of pattern had been, in his words, unconvincing. It was a cosmic paradox, and nobody could figure it out. So to crack this code, Hubble knew he needed to gather two key clues for every nebula he could observe. First, how far away is it? And second, how fast is it moving? Now what's fascinating is that getting these two pieces of info was not equally easy, at all. Measuring velocity, that was actually pretty straightforward. You just analyze the light from the galaxy, see how its spectrum is shifted, and boom, you get what's called its radial velocity. But measuring the distance, oh, that was incredibly difficult. I mean, really, really hard. It meant hunting for specific types of stars, like Cepheid variables, inside these super faint, faraway galaxies, and then guessing the distance based on how bright they appeared. Even Hubble himself admitted his methods were rough and had to be applied with caution. And this is what he had to work with. This is Table 1, straight from his paper, the core data for just 24 nebula. That's it. In his own words, it was scanty material. Just a list of names and numbers. Not a lot to go on, right? Okay, let's look at a cleaner, simplified version of that data. Now check this out. For the nebulae that are relatively close, like NGC 224, the velocity is actually negative. That means it's moving towards us. But look what happens as we go further out. At 1,000,000 parsecs, the velocity jumps to a positive 920 kilometers per second, away from us. Go out to 2,000,000 parsecs, and it's over 1,000. Are you starting to see the pattern here?
But here's the thing. The real genius here wasn't just in collecting this messy data. It was in what he did next, how he decided to look at it.
Because when you just look at them in a table, they're just numbers. The secret isn't jumping off the page.
But what happens when you take those two columns, distance and velocity, and plot them on a simple graph? This is the big reveal. This is Figure 1, probably the most important chart in the whole paper. You've got distance along the bottom, velocity up the side. And just like that, all the chaos just disappears. The data points don't make a random cloud, they line up. They form a clear line rising from left to right. And this wasn't just some random trend. This was a rule. That straight line on the graph, it represented a fundamental principle of the cosmos, a secret that had been hiding in plain sight, right inside that scanty data all along.
Hubble even did the math and calculated the slope of that line. He figured it was about 500 kilometers per second of velocity for every 1,000,000 parsecs of distance. And that number, that rate of cosmic expansion, would go down in history as the Hubble constant.
So this simple graph was way more than just a neat pattern. It was the first real, hard evidence for a completely revolutionary new idea about the nature of the universe itself.
So, what did this straight line really mean? Well, first off, this wasn't some minor effect.
Hubble himself said this relationship appears to dominate how galaxies move. All those other little random motions, that was just noise. The main thing happening was a single, systematic expansion of the entire universe. It was also the first real-world data that seemed to back up some of the wilder ideas coming from Einstein's theory of general relativity, like the de Sitter effect, which talked about a curved, expanding spacetime.
But you know, what I find maybe the most incredible thing about this whole paper is Hubble's restraint. I mean, he's sitting on a discovery that he knows is going to make him a legend. And how does he end the paper? With total scientific humility. He basically says, it's premature to discuss in detail the obvious consequences of what he found. He knew how big this was, but he just let the data speak for itself. Amazing.
And boy, did that data speak. Before this paper came out, the common view was that the universe was static, unchanging, eternal. And in just 6 pages, Hubble completely shattered that idea. He gave us a universe that was alive, that was dynamic, evolving, and expanding.
And this incredible discovery left the entire world of science with a profound and, frankly, unavoidable question. Okay, if everything is moving apart from everything else today, what happens if you run the clock backwards? If the universe is expanding now, what does that imply about its distant past? And maybe, just maybe, its very beginning?